Welcome to EDU World Space.
In this problem, we have a ring here that has a uniform charge distribution on it, lambda. And we're asked to figure out what the voltage is along an axis out of the page at the center of the ring. So I guess I could draw a little side view of it. So here's our ring, and then here's the z-axis here. And then the distance here, capital R, or I guess I used little r. This is capital R. So, this distance here is then z squared, square root of z squared plus capital R squared is the distance. So, what we're doing here is we need to integrate figure out each little bit of charge here, how much little bit of voltage it contributes to a point along the z-axis. So we need to integrate, and we can have our integral is given by this expression here, as usual, and then we know that dq is the charge density times the differential area or differential length element along which it acts, and that's r d phi. So that's again this differential length here is the radius times the differential angle. We also know that lambda is uniform, so that this is the total charge divided by 2r pi, or pi d. This is the circumference. Now, we can then, let's see here, we can plug this into here. And now we can do this integral, and this integral is really easy because nothing in here depends on phi. So we just integrate from 0 to 2 pi, and then do a little simplifying. We use this expression back in here, so we get that the voltage is given this way. So it's the total charge on this ring divided by 4 pi epsilon naught, of course, and then divided by the distance above the center we are. Now, no, not the distance above the center, distance from the from whatever, well, we're the same distance from any part on here as if we stay on this axis. So the distance we are from where we're looking at to a point on the ring is this value here. So that's our voltage. And now they ask for the electric field, or the magnitude of it. So the magnitude of it in the z direction, again, as we move up here, is just the negative of the derivative of the voltage, in the derivative in the z derivative of the voltage. So we can do that. We can take that derivative, and we get this expression here. So our electric field is, our constant here times z times q, the total charge, divided by z squared plus r squared to the 3/2. And so we can look at this and say, well, okay, if the charge is 0, then we have no electric field, right? Makes sense. Then we can see as we increase, when z is 0, we see that we have a 0 electric field. Okay, we don't have a 0 voltage though, because it's just that the gradient of the electric field of the voltage at 0 happens to be 0. And we can see that's basically because this is an even function of z. Basically, if we're down here, we have the same value up here. So we've got some even function. So when we go through the plane of the ring, we have a 0 slope. And so that means the electric field is going to be 0 there. And so the electric field, this is obviously a vector. This is the z component of the electric field, and we can see that it's positive up above and negative down below. Okay, I think that's all there is to really say about this one.